Here we are at example 9 from our 1.5 number 2 set of notes. Now there are a couple of ways that we can go about this problem. I think for right now I'm going to go ahead and show the formal way, but at the end of the video I'll probably show kind of like the nice quick shortcut for us as well. Now when we're discussing the limit as x goes towards infinity of this square root, we know that we can go ahead and actually break this up, where we have the limit as x goes towards infinity of the square root of this x cubed plus 7x on top, and then likewise we have the limit as x goes to infinity of the square root of 4x cubed plus 5. So pretty much just breaking up that radical and applying their own limits. Now when we're looking at our particular radicals, nothing unfortunately can go ahead and cancel. So as a result, we're actually going to go ahead and do a little bit of a foo. The cancellation can happen, but we're going to use that for our short end method. This I kind of want to show things a little bit more formally. What you would have to divide the top and bottom both by, if you try throwing in infinity, it won't work. By the way, you'd end up with that infinity over infinity in determinate form, so unfortunately that's out. But what we're actually going to divide the top and bottom both by is the x raised to the third halves power. And the reason why it's 3 halves power is because we're dividing it by that exponent of 3, so that would take care of the cancellation part, but we can only do that when we have our bottom, our denominator, being 2, because we're actually taking the square root of this. So we're actually dividing this entire piece by x raised to the 3 halves, likewise the bottom by x raised to the 3 halves. And that actually allows us then to be able to divide that evenly. So we have the limit then as x is going to infinity of the square root of x cubed plus 7x all over the square root of x cubed, because again this is really how we can rewrite that, and this is all over the limit as x goes to infinity of 4, the square root of 4, x cubed plus 5, all over, again, that same bottom, square root of x cubed. Now the reason why we would do that is such then that we can go ahead and combine these under one radical. So then we end up with the limit as x goes to infinity of the square root of x cubed plus 7x all over x cubed. And on the bottom, we have the limit as x goes to infinity of the square root of 4x cubed plus 5 all over x cubed. Simplifying this even further, we end up with the limit as x goes to infinity. Now we can go ahead and combine the tops and the bottoms. And right here we see that cancellation happening at, where we end up then with the square root of x cubed divided by x cubed is 1. Over here we'll just end up with a plus 7 over x squared, because this x would have canceled out with one of these x's down here, leaving us with x squared on the bottom, divided by the limit as x goes to infinity of the square root. Same thing's going to happen here. The x cubes are going to cancel out with that x cubed. When we're just looking at this piece, leaving us with just this constant in front, that 4, plus our 5 over x cubed. Nothing can be canceled there. Now we can go ahead and apply our limits inside of those nth roots. So we end up with the limit as x goes to infinity of this 1 plus 7 over x squared, and then our nth root, the square root is on the outside, all over the square root of the limit as x goes to infinity of 4 plus 5 over x cubed. And then going ahead and applying this limit to each item, we would end up with the square root the limit as x goes to infinity of this constant 1 is just going to be that constant 1 by definition. Likewise, when we throw in infinity into this piece, we'd have 7 over infinity. So that'll actually just reach that limit of 0 so really we're adding 0 to them, divided by square root of applying this limit as x goes to infinity. This constant 4 is just literally that 4, plus this bottom's going to get really, really large, so we have 5 over something really large, which is going to be a limit of 0. Simplifying things, we end up with 1 plus 0, the square root of 1 really, which is just 1, over 4 plus 0 is 4, square root of 4 is just 2. So it looks like our limit comes out to be 1/2. Now, that's the long using every definition and all that, breaking stuff up, applying limits, all that. That's the long way. And I wanted you to see that so you can see it step by step and why things are working the way that they're working. There is a dramatic short way to do this. And hopefully you guys have maybe kind of already seen it at this point. Now, right now, just looking at this thing from scratch, from the very beginning, we notice that we have the square root of x cubed plus 7x divided by 4x cubed plus 5. Well, just like when we were talking about end behaviors with, you know, regular polynomials, it kind of goes the same way also with functions. So we really only care about our highest degrees. All right? And as a result, we can then just take the limit as x is going to infinity here of the square root, and then pretty much just simplifying our highest degrees. Like if this is the only thing that's really going to matter, I mean, these guys we saw are just going to go to 0, so they really don't even matter. So if we just simplify this, really we have a 1 in front of this x cubed, and these x cubes will just cancel out, leaving us with just 1 over 4. And really, the square root of 1 over 4 is just 1/2. Because, you know, you could take your square root for each one and then just end up with square root of 1 is just 1, square root of 4 is just 2. Limit now as x goes to infinity of 1/2, that constant just comes out to be 1/2. And so as a result, you can see that you end up with the exact same answer with a lot less work. All right, so when you guys are actually doing these AP type problems, definitely look and see if you can do any kind of shortcut like this, because it will definitely come in handy. But again, though, that is example 9 from our 1.5 number 2 set of notes.